Assalamu alaikum students. I hope you are fine and must be good with your study and enjoying with good health. And I have delivered about 3 lectures about that linear programming, and particularly about that graphical method of solving the linear programming problems. Today will be our last lecture for this particular topic, and thereafter we will discuss some other methods of using that linear programming method. But class, in the last lecture we discussed about the different problems and we analyzed them, and finally we solved them in order to find the optimum solution in the particular operation settings. So you must know about the importance of that program, that how we can achieve the primary objectives of the organization, that is the profit maximization or the cost minimization. So important is the topic of linear programming, and you must be well aware of that how we can draw that objective function and how we can convert the different constraints or limitations in the organizational settings in the form of equations or the inequalities, and finally how we can draw those constraints in the form of graph in order to find the corner points. We discussed 2 very important topics, that is the ISO profit line method or the ISO cost line method in case of minimization, and the corner point method, that how we can find out the corner points in these sort of problems to find out the optimum solution. So there is no other solution sometimes feasible other than we find this through this particular method. So this is the importance of linear programming. It always helps us to take particular decisions, and in order to solve the particular problems which can be faced by the managers in the organizational settings. So it is very important for you people to do particular practice for these questions, and you should always solve the related problems to have a good practice about these problems, about the graphical method of solving the linear programming techniques. Today, again, as I said, this will be our last lecture for this particular topic, that is the graphical method of linear programming, and again we will discuss some important problems. So you should have the idea, and you should be well aware that how we can draw the different lines in order to find the optimal solution. Today we'll also discuss if there are more than 2 to 3 lines, like 4 lines we'll have to draw on that graph, and again the method is same. Again we will use that corner point method or the ISO profit line method to find out that optimal point, and to maximize the objective function of the organization. Again, that is the maximization of the profit or minimization of cost. Let's start our today's lecture with a very simple example. The Galaxy industry production. This example is about the Galaxy industry production, who is manufacturing 2 toy models, that is Space Ray and Zapper. So these are the 2 products which that particular company is producing. The resources are limited to. So again, these are our constraints, that is 1200 pounds of special plastic available for the manufacturing of these 2 products, and again 40 hours of production time per week. The total production time available for Galaxy industry production for the production of these 2 products, Space Ray and Zapper, is 40 hours. So of course we cannot work beyond that time limit. So this is one of the constraints related to the production time. Again, you know that there may be the different requirements on the part of the different departments. One of the marketing requirement in this particular topic is that total production cannot exceed 800 dozens. So again, we cannot have the production more than 800 dozen units. In this particular case, we are taking that production unit in dozens. It is very important, class, sometimes to be very careful about the units of measurement, because we should always have homogeneous units of measurement if we are formulating and identifying the different constraints. So keep in mind the units of measurement in case of profits as well as in case of constraints. The next requirement, marketing requirement, is that number of dozens of space rays cannot exceed number of dozens of zappers by more than 450. Now class, again this is a very important constraint, and we just have read out the two very important constraints. And again, if we consider this particular example, and again we'll have to decide about the decision variables. Now suppose there are two decision variables, that is the x1 and x2. x1 is relating to the production of space ray, and x2 is related to the production of zapper. So we have supposed that we are producing x1 units of space ray and x2 units of zapper, so that our profit will be maximized. And of course we'll have to find the value of these unknown decision variables, that is x1 and x2. Now class, total production cannot exceed 800 dozens. It means one of our constraint will be what? That will be x plus y, or x1 plus x2. If we consider those decision variables as x1 and x2, then x1 plus x2 should be less than or equal to 800 dozens. So that is our production related constraint. Okay, the other constraint, again, we cannot exceed the production of space rays by more than 450. Now what is this constraint about? That it can be represented in the form of inequality, like x1 is less than equal to x2 plus 450. Now that is the constraint. Again, please note down, students, x1 is less than equal to x2 plus 450. Now this is the constraint about this particular marketing requirement. Now again, if we say that it is x1 less than equal to x2 plus 450, we can again take x2 on the other side of the inequality, and we can have the final constraint as x1 minus x2 less than equal to 450. So this is about this particular constraint. Then there are some constraints about the technological inputs, that is space rays requires 2 pounds of plastic and 3 minutes of labor per dozen. The other requirement is zappers requires 1 pound of plastic and 4 minutes of labor per dozen. Again, we have one of the constraints relating to that special plastic, that we cannot use special plastic more than 1200 pounds. So if space rays takes 2 pounds of plastic and zapper takes 1 pound of plastic, so our next constraint is 2x1 plus x2 should be less than equal to 1200 pounds. That is the constraint about plastic. The next constraint is about hours of production. Now again, if space rays takes 3 minutes of labor per dozen and zappers takes 4 minutes of labor per dozen, then again we have the constraint as 40 hours. Now again, students, this is a very important point here, that we are given the constraints related to that production time in minutes. That is, the minute is the unit given in the constraints. But in this particular example, the total capacity is given in the form of hours, that is the 40 hours. So we'll have to convert these hours into minutes to have the homogeneous units in case of the constraints, as well as in the case of maximum available production hours. So again, class, this is a very important point to note here, that we'll have to convert these 40 hours into minutes. So if we multiply these 40 hours by 60, we can convert into the minutes. So 40 hours means there are 2400 minutes available for the production time per week. So what we'll do, we will convert these production hours into the homogeneous units, that is minutes. So this will be related to our fourth constraint in this case. So there are 4 constraints in this particular example. Now current production plan calls for producing as much as possible of the more profitable product. Space ray, $8 profit per dozen. Use resources left over to produce zappers, $5 profit per dozen. So this information is related to our objective function. So what will be our objective function equation? That will be equal to z. If we represent that objective function by z, then that z will be equal to 8x1 plus 5x2. So this is our objective function. The current production plan consists of, okay class, we have discussed in the previous lectures that there are two types of decision making. One decision is based on the perception or the intuition or the observation of the managers, but that may or may not work. The most important decision is that decision which is always taken on the basis of certain facts and calculations. So again, in this particular case, the space, there is a production plan before that operation manager that he should produce 100 dozens of zapper and 550 dozens of space rays, so that he can earn $4,900 per week. So this is the production plan in the mind of managers. But again, we will check out with our linear programming technique that whether this production or this production plan will give you the optimum solution or not. So that is very important, because this production plan at this point of stage is just on the basis, maybe just on the basis of observations. So class, a linear programming model can provide an intelligent solution to this problem. So in this particular case, we should not rely on that particular observation made by production manager, but we should rely some good technique like linear programming technique in order to find the optimum solution for the production of these two particular products, so that we are able to maximize our profit. So class, there are two decision variables again in this particular case, as we have already discussed that x1 is equal to the production level of space rays in dozens per week, and x2 is equal to production level of zappers in dozens per weeks, and our objective function is weekly profit to be maximized. So we'll have to maximize our weekly profit, and our objective function in this particular case, as we discussed, is 8x1 plus 5x2. That is the objective function for this particular example, and we are having 4 constraints. The constraint, as we discussed, relating to that plastic material is 2x1 minus x2 is less than or equal to 1200. The next constraint is related to the production time available, that is 3x1 plus 4x2 should be less than or equal to 2400. Again, for this production time, we have converted that total capacity into the minutes, so that is important. Then the next constraint is related to the total production, that is x1 plus x2 should be less than or equal to 800. Then there is another constraint which we discussed, is x1 minus x2 is less than or equal to 450. So these are the 4 constraints, and we will have to maximize the objective function by fulfilling all of these limitations or constraints. Again, xi is greater than or equal to 0 means if I is equal to or j is equal to 1, 2, then it means x1 and x2 is greater than or equal to 0. These are our non-negative constraints. It means that x1 and x2 cannot be in negative. These should always be equal to 0, or this should be greater than 0. So the set of all the points that satisfy all the constraints of the model is called feasible region. So again, you have already practiced that first of all we'll have to find out what is the feasible region in the problems by using that linear programming method. So using a graphical representation, we can represent all the constraints, the objective function, and the 3 types of feasible points. Now again class, let's start drawing those particular lines on the graph. Now again, we have taken that x-axis, the x1 on the x-axis and x2 on y-axis, and this is our first line equation that is related to the plastic constraint, that is 2x1 plus x2 is less than or equal to 1200. Now as you already know that how we will draw this line, that is we will put first x1 is equal to 0, we will get the value of x2, and then we will put x2 is equal to 0 and we will get the value of x1. So we will got the 2 points on x-axis and the y-axis, we will connect these points, and then finally we will have this sort of equation. in the form represented by that straight line. So as we are concerned with less than equal to constraint, so this is the particular area which is feasible for this particular line. Suppose we are at this point of time, we are only consider this line. So this is the feasible area for this line, that is the less than area for this line. Now if we draw the second line, that is the production time constraint, so for this particular line, the second line, all of the area below that particular line will be the feasible area for the second line. But actually we are interested in the area which is less than for both of these lines. So this will be again the common area which is less than both of these two lines. Then again there are two more constraints we'll have to draw on this graph paper. This is the third constraint related to the total production constraint, that is x1 plus x2 is less than or equal to 800. So again we draw that line, and again the feasible area, this one is the feasible area which is less than for all of these three lines. Now this is the last constraint related to that production mix constraint, that is x1 minus x2 is less than or equal to 450. So class, you have seen that we were having four different constraints in this particular problem, and we find out the feasible region for all of these four constraints represented by the straight lines on this particular graph. So this is our feasible region. Now we are interested, we have find out that feasible region for our particular problem, but we are interested in the solution which will give us the optimal achievement of that objective function. So let's consider this feasible area we have just computed. This is again our feasible region, and again if we consider that ISO profit line method in order to find the optimal point on this feasible region, then you have known that we will put profit equal to any of the arbitrary value. We will take profit equal to any arbitrary value so that we can have the profit line within that feasible region. So in this particular case, if we take that profit is equal to 2000, so we will have get this particular line. So again in the profit function we will put that profit function equal to 2000. Then by putting x1 is equal to 0 and then x2 is equal to 0, we will have the 2 points, and we can draw this profit line which is within the feasible region. Then again if we increase that profit up to 3000, we will have another point. Up to 4000 we will have another parallel profit line again within that particular region. So if we are going to increase that profit by a particular amount, we will get these sort of parallel lines, and finally we will get the line which touches the last peak point of our feasible region. So this particular point is actually our optimal point, because the outermost profit line touches the outermost feasible area at this particular point. And if we find out the values of x1 and x2 on this particular point, we will get that the profit is equal to $5040. So this is actually our maximum profit at this particular point. Let's have a more clear view of that feasible region. Now this is our feasible region, and if we represent this particular point at here so that we can have a more clear view, and we will move these profit lines away from the origin. And finally, if the profit line goes away from the feasible region, so we are not interested in that particular profit line which is away that particular feasible region. So this is the right profit line which touches the last point on that feasible region. So class, again if we point out the corner points, this the method we just have discussed was related to the ISO profit line method, and we can always use the other method like the corner point method, in which we identify the different corners on this particular graph. In this particular case, our corner points will be 0 or O, that is the origin, which have the coordinates 0, 0. The other point is A, whose coordinates are 0, 600. This is the particular point of relating to that corner point, and this is the other point B, whose coordinates are 480, 240, which are not yet known, but we will calculate this particular point by the intersection of the respective lines. And this is another point D, which is the corner point within that feasible region. So our feasible region is O, A, B, C and D. So what we will do, we will again first of all find out the points of intersection of the respective lines in order to calculate the coordinates of B and C, and then finally we will prepare a table for the different alternatives that by the different combinations of the two products X1 and X2, how we can maximize our profit. So this particular point is the intersection of these two lines, that is production time constraint and the production mix constraint, that is 2x1 plus x2 is equal to 1200 and x1 minus x2 is equal to 450. And now you people know that how to solve this particular equation by using that simultaneous method of solving equations. We will make equal any of the coefficients for any variable, either for x1 or x2, by multiplying a particular equation by a particular constant number. So then we will subtract these numbers, and finally we can get the 2 points in this particular case as x1 is equal to 550 and x2 is equal to 100. So this point of intersection is 550 and 100. In the similar fashion we will calculate the other point as well. That is the point B and C, and finally we will put all of these points in this particular table, and finally we can calculate our objective function by putting these values in this objective function. So you can see from this particular example that at this particular point, that is 480, 240, our profit is 5040, which is maximized. And if we compare this particular solution with this initial solution which was suggested by the production or the marketing manager, this is much better than that of the initial proposal made by the marketing manager. So you know that by using that linear programming, how we can maximize our profit and how we can optimally utilize our resources in order to achieve our primary objectives. So the profit will be maximized by producing space rays is equal to 480 dozens and zappers is equal to 240 dozens. There is no other alternative production level in this particular case through which we can maximize our profit. So this is the strength of that linear programming method. Class, let's discuss another illustration again relating to that linear programming method. A manager must decide on the mix of products to produce for the coming week. Now class, again as we have already discussed, that as a first step for solving these linear programming problems, first of all we will have to analyze a particular situation. And again I have told you that sometimes we said that if you rightly analyze the problem and you are able to find that what is actually the problem, then half of the problem is actually solved. So important is the analysis of a particular problem. So again, let's discuss that a manager must decide on the mix of products to produce for the coming week. Product A requires 3 minutes per unit for molding. So that is the again a requirement on the part of that product A. Then 2 minutes per unit for painting and 1 minute for packaging. Then product B requires 2 minutes per unit for molding, 4 minutes per painting, 4 minutes for painting and 3 minutes per unit for packing. So again class, as we read out this particular situation, to find out that there are 3 particular constraints in this particular example. One constraint is related to that molding, the other constraint is related to that painting, and the next constraint is related to packaging. Now there will be 600 minutes available for molding. Now this is the maximum capacity time available for these particular options, that is the molding and packaging and painting. So there will be 600 minutes available for molding, 600 minutes for painting, and 420 minutes for packaging. So it means that we cannot do the molding work more than 600 minutes, and the same is true for the other constraints. Both products have contributions of $1.5 per unit. It means that if you are producing 1 unit of product A, it will give us the profit of $1.5. Again, if we produce 1 unit of product B, it will again give us the profit of $1.5. So this helps us to formulate our objective function. Now what are the requirements? Algebraically or graphically state the objective and constraints of this problem, plot the constraints on the grid, and identify the feasible region, maximize the objective function. So again, in this particular example, what we want to do, we want to maximize our objective function. Now class, again, if we convert that particular statement in the form of the table by supposing that x1 is equal to the products A produced and x2 is equal to the products B produced, we'll have this sort of table. Again, product A requires 3 minutes of molding and product B requires 2 minutes of molding, and total molding time available, or the total molding time capacity, is 600 minutes. So again, this relates to our first of the constraint relating to that molding part. Again, the second constraint is related to painting, that is 2 minutes are being taken by the product A in case of that painting, and 4 minutes are being taken by the product B, and the total painting times available are 600 minutes. Again, in case of packaging, product A takes 1 minute, product B takes 3 minutes, and the total packaging time is available is 420 minutes. And this is the profit that if you produce 1 unit of product A, we will get the $1.5 profit, and if you produce one unit of product B, we will get the profit equal to $1.5. So this is the table which represents the whole of the situation in this particular illustration. Now class, again, we'll use that graphical method to state our objectives, and then to convert our constraints first into the different inequalities. So again, our objective function is 1.5x1 plus 1.5x2 subject to the different constraints. What are the different constraints inequalities? That is 3x1 plus 2x2 less than equal to 600. So this is related to our molding constraint. The next one is 2x1 plus 4x2 less than equal to 600. So again, this constraint is related to that particular paintings. The third constraint is x1 plus 3x2 less than equal to 420. That is the packaging constraint. So these 3 constraints are represented by equation 1, 2 and 3 in this particular example, and again x1 and x2 cannot be negative, so these are our non-negativity constraints. Now again class, just remind the method of solving these problems. You know, first of all, we'll have to draw these lines on the graphs, which represents actually the constraints available in this particular situation. So first of all, let's find out the 2 particular points for this constraint, that is 3x1 plus 2x2 is equal to 600. First we will put again x1 is equal to 0, we will get x2 is equal to 300. So we'll get one of the point 0, 300, which is actually the y-intercept. So this is the point at which this particular line will intersect the y-axis. Again, we will put then x2 is equal to 0, we will get the value of x1 as 200. So we'll get a point as 200 and 0, that is the x-intercept, that is the point at which this particular line will intersect the x-axis. In the similar fashion, we will find out the 2 points for the other 2 constraints. we will convert that inequality into the equality, and we will put again x1 is equal to 0, we will get x2 equal to 150. So this is the point, and again if we put x2 is equal to 0, we will get x1 is equal to 300. This is the second point. Again these points represents the y-intercept and the x-intercept for this particular constraint, which is now represented in the form of equation. Let's take the example of third constraint, that is x1 plus 3x2 is equal to 420. So we will put x1 is equal to 0, we will get x2 is equal to 140, which is the y-intercept. And again we will put x2 is equal to 0, we will get the value of x1 equal to 420. So this is the second point. And again if we, so class, we got the 2 points for all of these three equations. And now in the next step, if we use that ISO profit line solution method, so you already know that we will put that objective function equal to any of the arbitrary value. In this particular case, let's we take that arbitrary value equal to 150. Now again you can take any other value other than 150, but that profit line should lie initially within the feasible region, so that is important. So in this particular case we take that profit value equal to 150. If you put again this value of 150 in this objective function, we will get the objective function as 1.5x1 plus 1.5x2 is equal to 150. So this is the arbitrary value for we have taken for drawing that ISO profit line. So we will put x1 is equal to 0, and we will get the value of x2 is equal to 100. So this is the point on y-axis, that is 0, 100. Again in this profit equation we will put x2 is equal to 0, we will get x1 is equal to 100. So this is the x-intercept. Now class, again we'll have to draw all that constraints on the graph, and then we'll have to put that profit line on the graph to find out the optimal point. Now again this is the x-axis, this is the y-axis, and you have taken any suitable and convenient scale on both x-axis as well as y-axis. And first of all we will draw the first line. So this is our first line equation, that is 3x1 plus 2x2 less than or equal to 600. Now because we are interested in that constraint of less than or equal to, so our feasible region will be less than of this line. If we consider only this particular line, our feasible region will be this one, that is the less than region of that particular line. Now in the next step we will draw that second line, which is actually the painting constraint, and again the feasible region for this particular line will be less than area, and this one is the area which is feasible for both of these two lines. Now this is the third constraint, that is x1 plus 3x2 less than or equal to 420, which is the packing constraint, and again this is the area which is less than all of these three lines. So this is our final feasible region. Now in the next step we will have to put that profit line which we have just computed on this graph. Now this is the profit line where the x1 and x2 will be equal to 100, which we have just computed. And again class, if we point out the different corner points in this particular graph, these are the four corner points in this particular case. So again the optimum solution can be found on corners, and it is just said by that corner point method that we will always be able to find our optimum solution at any of the corner points. So again if we use that ISO profit line method, what we will do, we will draw or move that profit line away from the origin until it touches the last point of that feasible region by putting or by taking the different arbitrary values. So this is the particular point where that profit line touches. If we move further this profit line, then it will go beyond the feasible region, which is not actually the point of calculation in this particular case. So this is the optimal point in this particular case. Again class, what are the different corner points? One is the origin again, where x and y axis is equal to 0. The other corner point is A. The next corner point is B. Third corner point is C. And the last corner point is D. So our profit will be maximized at any of these corner points, which we have already actually identified through that ISO profit line method, which touches at the point C. So now we will calculate the coordinates of these points of intersection by solving the respective equations, and one of the corner point B is the intersection of following two lines. So we will solve these following two lines, and you already know that how to solve these equations simultaneously. That is, we will multiply any of the equation by a particular number so that we can equate the coefficients of any of the decision variable, and then thereafter we can subtract these equations to find the value of the other decision variable. So if we solve these two particular equations, we will get the value of x2 is equal to 120. And again, if you put the value of x2 equal to 120 in any of these two equations, we will get the value of x1, and so we find the coordinates of point B as 60 and 120. In the same fashion, we will solve for the other corner point C, that is the intersection of these two particular lines, that is 3x1 plus 2x2 less than equal to 600, and 2x1 plus 4x2 is less than equal to 600. Again, we will equate the coefficients of any of the decision variable by multiplying by a particular number to either one equation, or sometimes it may be required to multiply both of these equations, but we'll have to equate actually the coefficients of both of these equations for any of the decision variable. So again, if we solve these two equations by that simultaneous method, we will get the value of x1 is equal to 150. Again, by putting the value of x1 in this equation, we can get the value of x2 is equal to 75. So these are the coordinates of the second point C, that is 150 and 75. Now class, we have the coordinates of all of the particular corner points. We were having 4 corner points in this case, that is O, A, B, C and D. The coordinates of O, A and D were already known, and by using the simultaneous equation method, we just computed the values of the coordinates for the point B and the point C. Now this is our profit function, that is z is equal to 1.5 x1 plus 1.5 x2. Now what we will do, we will put these values of x1 and x2 one by one in this particular profit equation, so we can get the different alternatives. Again, if we put the coordinates 0, 0 in this profit equation, we will get the profit equal to 0. So that is the arbitrary point, and we are actually not interested in that particular point. The next point is the A, where x coordinate is 0, y coordinate is 140, and we will put these values in this particular profit equation. We will get the profit equal to 210. Again, what is meant by this particular alternative? It shows us that if we do not produce the product x1, and if we only produce product x2 and exactly the 140 units of x2, then we will get the profit equal to 210. Again, at the point B, if we produce 60 units of product A and 120 units of product B, we will get the profit equal to 270. Point C, if we produce 150 units for product A and 75 units for product B, we will get the profit equal to 337.5. And again, at the point D, if we produce 200 units of product A and we don't produce for product B, then we will get the profit equal to 300. Again, what is the maximum profit? That is 337.5, which can be achieved by producing 150 units of product A and 75 units of product B. So this is our maximum profit available by using the respective alternative of production. Let's take another example. A company wants to produce at most 1800 units of a product. So class, in this particular statement, again we have a sort of constraint. That is, a company cannot purchase more than 800 units of a product. There are two types of the product M1 and M2 available. That is, M1 occupies 2 foot cube, it costs ₹4 and the company makes the profit of ₹3. M2 occupies 3 foot cube, costs ₹5 and the company makes the profit of ₹4. If the budget is ₹5,500 and warehouse has 3,000 feet cube for the products, now what is being required? Formulate the problem as linear programming problem. So again, we'll have to find the optimum solution. We'll have to maximize our profit function in this particular example again. So class, let's have a view on this particular example. First constraint is represented by 800 units of a product. That is, they will have to purchase at most 1800 units of a product. So this is the first constraint. Then the other constraints are represented by that foot cube. That is, what actually space a particular product takes. That is being represented by a unit of that feet cube. Then the cost dimension is given for the different products. Again, we'll have to produce the products within that cost limitation. And again, the company makes the profit of ₹3 for the product M1 and makes the profit of ₹4 for the product M2. So these two values represents our objective function. So again, after analyzing the situation, we have the idea that we have some profit maximization function and we are interested to maximize the profit function. Then there are some constraints, and of course we'll have to represent these constraints in the form of inequalities. Now again, if you put that all information available in that particular problem in the form of the graph, then it is always easy to formulate the profit function as well as to formulate the equalities or inequalities for the different constraints available for a particular problem. So if we suppose that x1 is the total number of products M1 produced and x2 is the total number of products M2 produced, then again the area limitation is given as 3000, and of course we cannot go beyond that limit of 3000. So in this particular case, our constraint inequality will be 2x1 plus 3x2 less than or equal to 3000. Then again, cost function, product M1 takes 4 rupees for producing and M2 takes 5 rupees for producing, and total resources available are 5500 rupees. And of course we'll have to represent this particular information in the form of inequality, and that will be 4x1 plus 5x2 less than or equal to 5500, and our profit function will be 3x1 plus 4x2. That will be our profit function. And additionally, company wants to purchase at most condition, that is 800 units of a product. So this is another constraint, that we cannot produce more than 1800 units of a product. So again, in this case, our decision variables are x1 and x2, and our profit for product M1 will be equal to 3x1, and our profit for product M2 will be equal to 4x2, and our profit function will be equal to 3x1 plus 4x2. Now let's formulate the constraints of the problem. For the area, the maximum availability is 3000 feet cube, and area required for M1, which is represented by x1 in this particular example, is 2 foot cube, whereas for the product M2, x2 is 3 foot cube. So the constraint becomes as under, that is 2x1 plus 3x2 should be less than or equal to 3000 feet cube, and that is actually the first constraint related to that area. Similarly, for the cost, the maximum availability is ₹5500. Product x1 required ₹4 per unit, and product M2 represented by x2 required ₹5 per unit. So the constraint becomes as 4x1 plus 5x2 less than or equal to 5500. So this is our second constraint related to cost. Now there is another third condition represented in the form of limitation or the constraint, that is company wants to produce at most 1800 units of a product. This is the production constraint, that the company must produce at most 1800 units of the product, and the product is composed of X1 and X2. So this particular constraint may be represented. So this particular constraint may be represented by the inequality as X1 plus X2 should be less than equal to 1800. So class, this is the another constraint which is actually relating to that production requirement. Again, we will have to add non-negativity constraints or the restrictions. The decision variables should be non-negative, which can be expressed in mathematical form as under, that is x1, x2 greater than equal to 0, because the values of x1 or x2 cannot be in negative. We are actually talking about the quantity of the product x1 and x2, and of course the quantity cannot be in negative. So this is our non-negativity constraint actually. So class, this is the whole analysis of this particular situation, that is the profit maximization function is z is equal to 3x1 plus 4x2 subject to the three different constraints related to area, cost and product or production constraint. The first constraint related to area, as we have just computed, is 2x1 plus 3x2 should be less than equal to 3000. The second particular constraint related to cost is 4x1 plus 5x2, that is less than equal to 5500, and third particular constraint is related to that production constraint, that is x1 plus x2 should be less than equal to 1800. So these are the three different constraints. Again class, I will not solve this particular example, and I will leave this example for you people. First of all, again you should have to draw the graph. You'll have to draw the particular lines for these three particular constraints related to area, related to cost, related to 1800. You'll have to find then the feasible region which will satisfy all of the three constraints. Then again, you may use the ISO profit line method. You'll have to draw that profit line on that feasible region in order to take, or by taking any of the arbitrary value for that profit function. We have already practiced for these similar problems, and again in this maximization problem we will try to move away that profit line, that is moving away from the origin, and finally the point at which that profit line will touches the outermost area of the feasible region, that will be our optimal point at which our profit will be maximized. Again, you'll have to identify, and you'll have to use that corner point method to identify the different corners, and again, as the corner point said, that our profit will only be maximized at the corner points, and then that of course will include one of the point which we have just identified through that ISO profit line method. So after identifying those corner points, you'll have to find out the intersection points by solving the relevant equations. So then you will be able to find the final alternative table in which you will compute the different alternatives available for this production plan, and finally you will be able to find out that by using what level of production level for the two different products x1 and x2 we can maximize our profit. So class, this is the example I am leaving for you. I have already computed the profit function, the different constraints converted in the form of inequalities. So I don't think that it is very difficult to solve this particular example. So just have a practice in this particular example. So class, this was our fourth lecture for this particular topic, that is the graphical method of linear programming. As this is a very important topic, so I spent as much as 4 lectures for this particular topic. We have done about 9 to 10 or more problems relating to the linear programming by using that graphical method. Now you people should further practice the different other problems, again from your textbook, from the internet, or some other books in which some problems related to the linear programming methods are given. So after practicing, you should be able to solve any of the problem relating to that production plans or relating to any other situation which is related to that linear programming situation by using that graphical methods. But again, there are also some assumptions in which we cannot use the graphical method. Most importantly, if there are more than 4 to 5 or 6 equations, then it is very difficult to draw the graphs for the each and every line, and sometimes we use some other methods for solving these sort of linear programming problems, and that method is generally referred as Simplex method. So in the next coming classes, we will discuss another method of linear programming which is called as Simplex method, and again this is a sort of iteration method and uses some step-by-step procedure in order to solve the similar problems. So from the next class onward, we will discuss this particular method of Simplex method. But I hope from you people that in this particular week you should take the similar examples. First you should solve again all the problems which we have just discussed in 3 to 4 lectures. Then you should solve some other related problems from the different texts, so that you have the expertise in solving that problems by using the graphical method. So class, this is the end of our lecture, and I hope you got this particular method of graphical technique of linear programming. Okay, take care and good luck. Stay blessed. Khuda Hafiz. Bismillah.